is going to be on the machine learning methods that we use to achieve this goal within Schrödinger. We'll be talking about using machine learning to predict the properties of not just small molecules, but also polymers and complex formulations, which are mixtures of multiple molecules and polymers into a single amorphous system. And we'll also be looking into how machine learning can directly impact the properties of the device level architecture that you're trying to design. We go from the atomic level all the way to the device level using machine learning. So from these different materials, we generate a feature vector, and these feature vectors can be generated based on cheminformatic techniques from smile strings, for example, or it could be generated using quantum mechanical approaches or molecular dynamics approaches. So once we get a feature vector for these different materials, we can try out different types of machine learning models, like a neural network, a tree-based model, or a linear regression model, and decide which are the best models for that particular application, for that particular material. So we have an automated tool called Deep AutoQSAR, which allows a non-expert in chemistry or machine learning to use these tools in a fully automated way. And the only thing that you need to bring is a data set. As long as you have a data set of 50 or more materials or molecules, you can upload this data set to our MS Maestro graphical user interface, and our Deep AutoQSAR will automate the process of creating these machine learning models for these materials. We also have a machine learning property prediction panel, which allows you to use pre-trained models to make predictions on a variety of different material science properties in a fraction of a second. But the main advantage of machine learning is that it allows you to make predictions in an order of fraction of a second. So you can actually scan through tens and thousands and millions of formulations as a first screening process before you go into validation with physics-based simulations with either molecular dynamics or with quantum mechanics. So the first example that we want to talk about is drug solubility in solvent mixtures. Say, for example, you've designed a new API and you want to come up with the right combination of solvents that will maximize the solubility of this drug in your solvent mixture. These are the results of using formulation machine learning approach, which I mentioned earlier is a fully automated approach which generates the cheminformatic descriptors based on the smile strings, and then it also takes into account the composition and combines this with the cheminformatic description, and it scans through an entire range of machine learning models and gives you the best performing model for this particular property. Can we predict the viscosity of a binary mixtures of organic materials? So this is a data set that was published a few years ago, and this contains a curated data set of around 34,000 temperature-dependent viscosities. So there were more than 1,300, close to 1,400 unique molecules in this data set, and you can see the examples of the molecules shown on the top right. And if you combine any of these two molecules at any given ratio, what is the viscosity? And we want to be able to do this with machine learning. And as you can see, the model is performing very well. It's able to capture nonlinear trends. It's not just a simple increase or a decrease. There's an increase followed by a decrease. And the neural network is able to capture these nonlinear trends in viscosity as a function of the different ratios of different materials and as a function of temperature. So now that we have these machine learning models for solubility and for viscosity, what are the type of interesting things that we can do with these machine learning models? How can this actually help us with formulation development? And that's why we came up with a tool called the formulation optimization, a formulation machine learning optimization panel, where you provide a list of ingredients, and you also provide a list of machine learning models that can accurately predict multiple different properties. So this is an example where we've applied this to really complex formulations. For example, for shampoo formulations, where you have a surfactant, a thickener, a polymer, a conditioning polymer, and water in your formulation. So let me jump into a more complex case study of using formulation machine learning for heterogeneous catalysis. So this is not a classical formulation. It's not really an amorphous mixture of different materials, but this is a more complex mixture in the sense that you have a substrate, you have a catalyst, and you have different reactive gases coming in, and you have different products coming out. So there are multiple materials involved in this entire experimental setup. Finally, I'd like to talk about using formulation machine learning, not just based on experimental data, but we can actually generate high throughput data with physics-based simulation. Most of the customers that I work with are dealing with small quantities of data. So with physics-based simulation, you can come up with really powerful descriptors that improve the accuracy of machine learning models, even for small data sets. But we can also generate hundreds and thousands of physics-based simulations and use that as the training data to create machine learning models. So this is exactly what we did in this case study, which is also a publication which was published a few months ago in NPJ Computational Material Science. So this is the publication shown on the bottom right. So in this publication, we started off by looking at different types of miscible solvents, for example, acetone and benzene, ethanediol and acetone. So we went through the CRC handbook and we looked at all the possible combination of miscible solvents, not just binary solvents, but up to 5 different solvents in a single formulation. So we are putting machine learning models, lower level machine learning models trained on quantum mechanical data, into higher level machine learning models trained on the device property data. So in addition to the materials features, we provide layer features like the dopant, the layer thicknesses as well, and we can also provide device features like the operational voltage of this OLED device. So by combining these cheminformatic or structural features with QM methods, we're able to get accurate models for a variety of different properties like the external quantum efficiency, the current efficiency, the ultroluminescence max, the chromatic index X and chromatic index Y. Instead of sticking to small-scale simulations of the order of few tens or few hundreds of atoms, we can do simulation on around 10,000 or 20,000 atoms with DFT level accuracy with the help of machine learning force fields. So we have a whole family of machine learning models based on organic systems. For example, we have a machine learning model where we correct the energies of XTB, semi-empirical approaches, using a machine learning method. And we've noticed that this works well for transition state and barrier energies. We have a specific force field for organic crystals. We have another set of force fields for inorganic materials that we've trained on the materials project trajectory dataset and the OMAT24 dataset. And we've also trained on combinations of both organic and inorganic systems. So we have hybrid force fields that can tackle both organic and inorganic systems.